So we'll start with mathematical logic. Okay. So mathematical logic is the foundation for deductive verification, right? So we're first going to look at this approach towards verification called deductive proving, right? And for that purpose, we will use mathematical logic. Okay. So we are going to use logic for multiple purposes. So given a program, right? In order to write the specification of the program, right? So the specification is what a program is supposed to do, right? So whenever you're writing a program, you have some task in mind, right? Some end goal in mind. So that's the specification of the program, and we will use logic for accurately and precisely writing down specifications of programs, right? So when you, for example, use testing, you use test cases, right, with some input and expected output. But test cases are finite, right, and limited in number. Imagine a specification, right, written in logic as a very succinct and precise way of describing the expected outputs for a large number of inputs, right, or even for an infinite input space, right? So you can do that using mathematical logic, right? So we are also going to describe program executions using mathematical logic. So we know that verification is the process of ensuring that a program always does what it is supposed to do without even actually executing the program once, right? So what we'll do is we will symbolically execute the program through mathematical logic, right? And in this way, we are going to reduce the verification problem, which means does every execution of the program satisfy its specification, to the satisfiability or the validity problem of logical formula, right? So these problems, right, satisfiability of logical formula, these are well studied, right? And there are decision procedures, right, which are essentially algorithms which take as input a logic formula and determine whether that formula is satisfiable or not, right? So we are going to use these decision procedures for verification, and the guarantees, right, that are given by logic will translate into mathematical guarantees of program correctness. Okay. So let's dive in now and discuss first the simplest form of logic, right, which is propositional logic, right? So we're going to go very slowly and build up the foundations of propositional logic. Okay. So in propositional logic, right, we ask questions like these, right? So we have some formula, right, and this formula uses a lot of symbols, right? So this formula that is being shown on the slide, right, it's using variables such as p and q and various binary connectives, right, such as and imply and so on. So given such a formula, we ask whether such a formula is valid or whether it is satisfiable. Okay. So let's try to understand, right, what all these variables mean, what are these logical connectives, and what do validity and satisfiability mean. Okay. So we will first start off with the syntax, right, for propositional logic. Okay. So let's go step by step, right. So the most the very first thing, right, that you need to understand about propositional logic is this notion of an atom. So an atom is either a truth value or it is a propositional variable, right? So truth values, there are just two truth values, either false or true. So we are going to use this symbol bot, right, in order to represent a truth, the truth value false, and this symbol called top in order to represent the truth value true. Okay. So both false and true are atoms, right? Similarly, every propositional variable is also an atom. So we are going to use symbols like p, q, and r for propositional variables. Okay. Now these propositional variables can be combined together, or in general, atoms can be combined together using logical connectives. So we have the usual logical connectives, right? And, or, not, implies, and if and only if. Okay. So and, or, and, implies, and if and only if, these four are binary connectives, right? So they take as input two atoms, right? While not is a unary connective, right? So it just takes as input a single atom. Okay. So when we say a literal is either an atom or it is its negation. Okay. So negation is obtained by applying the not logical connective, right, before an atom, right? So when I say something like not of p, then this is a literal. Okay. Similarly, p itself is also a literal, right? So either an atom or its negation is a literal. And finally, we define a formula as either a literal or the application of logical connectives to other formula, right? So this is an inductive definition of a propositional logic formula, right? So what we are saying is a propositional logic formula is either literal, right, or it is obtained by applying one of these 5 logical connectives to other propositional logic formula. So as an exercise, right, let's look at these 2 formulas and let's try to identify atoms, literals, logical connectives and sub formula, right? So both of these are propositional logic formulas, right? So what are the atoms in this formula? So we have P and Q, right? So P and Q are the atoms, right? Similarly, false and true, these are also atoms in the formula, right? All of these atoms are also literals, right? And furthermore, this not of Q, this is also a literal, right? So we have covered atoms and literals. Next we have logical connectives, right? So the first formula is using the logical connectives and an implication, right? So it's using the implication twice, okay, while the second formula is using and an implication as well as the logical connective or, okay. So notice that if you look at the first formula, right, so this first formula at the top level is obtained by applying this logical connective, which is implication, to 2 sub formulas, right? So what are the sub formulas? So this is the first sub formula and this is the second sub formula, right? So every formula is obtained by applying a logical connective to sub formulas, right? Similarly, this particular formula, right, this is obtained by applying the logical connective and to these 2 sub formulas, right, which is P and P implies Q, right, and so on, okay. So far we have seen the syntax of propositional logic formulas, but let's now try to understand the semantics, okay. So semantics is what gives meaning to propositional logic formulas, okay. So a formula by itself doesn't have any meaning, but using an interpretation we can give a meaning to the formula, right. So the meaning of the formula means is the formula either true or false, okay. So an interpretation I is defined to be this function, right. So we use, so this particular notation says that I is a function from the set of propositional variables to truth values false or true, right. So we take every propositional variable that's used in the formula and you assign either of these truth values, right, either true or false, okay. So this is what an interpretation is. So you can apply the interpretation I on some propositional variable P. So I is a function, right, and it will give either true or false, okay. So a given I will fix what is the truth value that's assigned to a propositional logic variable, okay, propositional variable. Now given an interpretation, you can now evaluate a formula, right. You can ask whether or not the formula evaluates to true under this particular interpretation, okay. So given an interpretation I and a formula F, either the formula evaluates to true or it evaluates to false. So we are going to introduce some symbols here for this purpose, okay. So let's look at the first symbol, okay. So this particular symbol is pronounced as model of, okay. So what it says is that I is a model of F if F evaluates to true under I, right, and I is not a model of F if F evaluates to false under I, okay. So which means that if we say that I is a model of F, right, then the formula F is going to evaluate to the truth value true under the interpretation I, right, and similarly if the formula F evaluates to false under I, then we are going to say that I is not a model of F, right. So now we have not yet defined how to evaluate a formula under an interpretation, right. So let's do that now, okay. So before going to define, or before defining the notion of an evaluation, right, let's introduce this notion of relations, right, in discrete maths, okay. So in fact this particular notation that we have defined, right, which is this models of, this is actually a relation, right. So what is a relation, right? So if you recall, right, a relation R, right, or a binary relation R is essentially a subset of a cross product between 2 sets A and B, right. So if you have 2 sets A and B, then a relation R is a subset of the cross product of A and B, okay. So it essentially relates an element of the set A to an element of the set B, okay, and it's a subset, okay. So now think about this particular models of relation, right? It is a relation, but between which sets, right? So what is it relating? So it's relating an interpretation, okay, with a formula, right? So you take the set of all possible interpretations and you take the set of all possible propositional logic formula, and now this models of relation, right, is a subset of that cross product, right? So first we are going to define the set of all possible interpretations and all possible propositional logic formula, okay. So let us take V to be the set of propositional variables, okay. So f of V is the set of all propositional logic formula over V, right? So we are introducing this notation which is f of V in order to indicate the set of all propositional formula over V, okay. So now this relation, right, which is this models of relation, is a subset of this cross product, right? So what is this cross product? So this notation, right, means we are considering all functions from V to true or false, right? So we know that an interpretation assigns a truth value, right, to every propositional variable, right? So the set of all possible interpretations is the set of all possible functions, right, which we denote using this particular notation, right, which is saying that this is essentially the set of all functions, right? So you take the set of all functions from the set of propositional logic variables V to the truth values true and false, okay. And f of V is the set of all possible logic formula, right, propositional logic formula over the variables V, right. So this is a relation which is a subset of these two, right. So it doesn't relate every interpretation to every propositional logic formula, right. It only relates those interpretations under which a formula evaluates to true, right. So if the formula evaluates to false, then these two, then the interpretation will not be related to that formula, okay. So for example, right, if you take let's say the interpretation I, sorry, so if you take the interpretation I which assigns P to, let's say, the truth value true, right, then this I is a model of the propositional logic formula P, right, but I is not a model of the propositional formula not of P, right. So again, thinking about it in terms of relations, right, you can say that I and the formula P, right, this particular tuple, it belongs to this relation, right, but I and not of P, it does not belong to this relation, okay, because I is not a model of not of P, okay, because under I, P evaluates to true, okay. So now you may ask this question, right, is this relation a function or not, right? So again, if you recall from discrete mathematics, right, a relation is a function if it assigns a unique value to every element of the domain A, right. So for every element of the domain A, if the relation associates an element of the domain A with a unique element of the set B, right, which is also called the codomain, right. So then this relation is called a function, right. So is this relation, right, which is this models of relation, is it a function or not? To answer that question, you need to think, right, whether is it possible that an interpretation could be related to multiple formulas, right? And indeed, right, it is clearly possible, right. So if you just take this particular interpretation itself, right, which relates P to the formula P to the propositional to the truth value true, okay, is there another formula, right, which is related to I, right, in the sense that is there another formula which also evaluates to true under this particular interpretation I, right? So I can simply take this formula true itself. So true by itself is a formula, and I know that under this interpretation I is a model of true, okay. Similarly, I can take something like P or P, right, and under this particular interpretation I, right, this formula is also going to evaluate to true, right, and there are in fact an infinite number of such formulas, right, which evaluate to true under this interpretation I, right. So therefore this models of relation, right, is not a function. Okay, it relates those interpretations to those formula under which the formula evaluates to true. Okay, so let's now try to define this notion of evaluation, right, more precisely. Okay, how do you evaluate a formula under an interpretation, right? So we are going to define the semantics inductively, right, which means that we will start with base formula, right, and then we will move on to compound formulas, right, which are formulas generated using other formulas. So these are the 4 base formulas, right. So I have so this should be not of P. Okay, so I have true, false P and not of P. Okay, so the first case, right, it says that if you take any interpretation I, right, so you can think of this as saying any arbitrary interpretation I, right. So any arbitrary interpretation I is a model of the formula true. Okay, so this means that I comma true, right, is going to belong to this particular relation, right, which is the models of relation. Okay, and no matter what interpretation you take, right, so this just says that this formula true always evaluates to true under any interpretation I, right. Similarly, this says that no matter what interpretation you take, it is never a model of the formula false. Okay, so there does not exist any I, right, such that I comma false, right, belongs to this models of relation, right. So if you take any interpretation I, it is never a model of the formula false. Okay, so this third one says that if I of P evaluates to true, right, which means that P is assigned the truth value true, then I is a model of P, right. Okay, I think okay, and the fourth one says that if I of P evaluates to false, then I is not a model of P. Okay, so if I of P evaluates to false, then I is not a model of P. So these are the 4 base cases. Let's now move on to the inductive cases. So the inductive case is where we will talk about evaluation of compound formulas, right. So these are the 5 ways in which I can generate compound formulas using sub formulas, right. So I can use any of these 5 logical connectives. Okay, so the first case says that I is a model of not of F if and only if I is not a model of F, right. So notice that here, right, this negation, right, this is a logical connective. So whether I is an interpretation of this entire formula, in order to evaluate that, you need to first evaluate F, right, using the interpretation I, and then see that whether or not the interpretation I is not a model of F, right. So if I is not a model of F, then I is a model of not of F, right. So similarly for and, or, implication and double implication, right. So let's just go through all the 4, right. So I is a model of F1 and F2, so of this entire formula, if and only if you first evaluate F1 under I and see that F1 evaluates to true under I, right. Similarly, I should also be a model of F2, right. So if I is a model of F1 and if I is a model of F2, then I is a model of the formula F1 and F2. Okay. Similarly, I is a model of the formula F1 or F2 if I is either a model of F1 or I is a model of F2, right. I is a model of F1 implies F2, so this is interesting, right. So I is a model of F1 implies F2, right, if either I is not a model of F1, right. So if I is not a model of F1, then you can just say that it's a model of F1 implies F2, or if I is a model of F1, then it should also be a model of F2, right. So by implication, what we want to say is that if I is a model of F1, then I is also a model of F2, right. So if I is not a model of F1, then clearly I is a model of F1 implies F2, right. But if I is a model of F1, then it should also be a model of F2. Okay, and for by implication, right, if I is a model of F1, then I should also be a model of F2, right, or if I is not a model of F1, then I should also not be a model of F2. So notice that what we have done is we have defined evaluation of these compound formulas using the evaluation over the sub formulas, right. So every time, right, we take a sub formula, right, and we evaluate the sub formulas under the interpretation I. Okay, so this is an inductive definition of the semantics of propositional logic. So let us take an example in order to understand this, right. So let's take this particular interpretation I. So it evaluates or rather it assigns the truth value true to P and the truth value false to Q. Okay, and under this interpretation I want to see whether or not this formula evaluates to true or false. Okay, so is I a model of F? Okay, so let us do this calculation, right? So so what is F, right? So F at its top level, right? F is an implication, right? So it's P and Q implies P or Q. Now recall what we just saw in the last slide, right? So in order to evaluate a formula which is an implication, right, you look at the sub formula that is before the implication and the sub formula that's after the implication, right? So the sub formula that is before the arrow symbol, right, this we call as the antecedent, and the sub formula that is after the implication, right, that's after the arrow, is called the consequent. Okay, so this is F1 implies F2, right, where F1 is P and Q and F2 is P or not of Q. Okay, so I is a model of F1 implies F2. In order to check that, there are two possibilities, right? Either I is not a model of F1, right, or I is a model of F2, right? So let's see, is I not a model of F1 here, right, which is P and Q. So we want to find out whether or not I is not a model of P and Q. Okay. So when will I not be a model of P and Q, right? So this is possible only if I is not a model of either P or I is not a model of Q, right? Now we know that I is not a model of Q, right? So I is not a model of Q. This is what we know, right? And therefore I cannot be a model of P and Q, right? Because if you look at the last slide, we said that I is a model of F1 and F2 if and only if I is a model of F1 and I is a model of F2, right? But here I is not a model of Q, and why is I is not a model of Q? Because Q, so to Q I has assigned the truth value false, right? So therefore since I is not a model of Q, therefore I is not a model of P and Q, and therefore I is actually a model of the formula F, right, which is P and Q implies P or not Q, right? So this is one way to reason about this particular semantics, right? So you can also look at the consequent, right? So you can also ask, is I a model of P or not Q? And again, right, because I is a model of P and I is also a model of not Q, right, because it assigns the truth value false to Q, therefore I is also a model of the consequent, right? So in either direction you can show that I is actually a model of this formula. So in fact, if you look at this formula very closely, right, you can say something more about this formula, which is that under no interpretation will this formula ever evaluate to false, right? So under every interpretation this formula is going to evaluate to true. Okay, and this is because if you take any interpretation, right, where P and Q is true, then obviously P or not of Q is going to be true, right, because P itself is going to be true, right? So there is no interpretation which will falsify this formula,